Okay, thank you, everyone. So, Привітання, Minsk. My name is Milica. I'm Vivid Digital on Twitter, if you care about that. I'm a contractor for Google. I work on web.dev, where I write about performance and developer tools. So if you're struggling with long load times or poor application responsiveness, we try to help with stuff like that. If you care about it, and I really think you should come talk to me after my presentation about problems you're facing and how we can help you solve them. I'm also a Mozilla tech speaker, and I used to be an intern at Mozilla on Servo browser engine. Parts of Servo are what makes Firefox fast today. It can do a lot in parallel, and it's able to do that because it's written in Rust. Rust is a cool new systems programming language, kind of like C or C++, but with memory safety. So I got to learn a little bit of Rust, and I really liked it, but I'm a web developer, and I really love the web. This was in 2017, when WebAssembly had just landed in the browsers, so I decided to learn more about it. In short, WebAssembly is a way to run code other than JavaScript in web browsers. I want to talk to you about how we got to this point, what issues JavaScript is having, and how WebAssembly can help solve them. I'll explain why we need it, and what does it mean for the future of web development. Chances are you already came across WebAssembly in the wild without even knowing it. I'll show you some cool examples and some very practical ones too, so let's get started. In every browser, whether you use Chrome, Firefox, or Safari, code is interpreted and executed by a JavaScript engine, which only runs JavaScript, at least until recently. But what about C, C++, or Rust? JavaScript is just not ideal for any problem we have to solve. That's where WebAssembly steps in. You do not write WebAssembly. You compile other languages to it. But why would you want to do that? Why do we need WebAssembly? The shortest answer is performance. And there are many cases where we really need performance, but I want to talk about one particular. And that's video games. Some of the very first WebAssembly demos were video games. In 2017, Unity published Tanks, which you could play in the browser. And then last year, someone ported Doom 3. And Unreal Engine, another browser engine, another gaming engine, also published this demo, which is the Japanese Zen Garden. Things like these need physics engines. They need to do a lot of mathematical calculations, recalculate positions of millions of pixels. And video games in general have to process audio and often implement artificial intelligence. These are cases where performance is really important, and that kind of performance is just hard to get from JavaScript. This is a screenshot of the first website ever, which Tim Berners-Lee published maybe 30 years ago. Back in that time, web was just text and links. JavaScript came about as a way to bring a bit of interactivity to the web. It was designed to be easy to learn and easy to write. But it wasn't designed to be fast. So over the years, browser engines added optimizations to the way they interpret JavaScript. We started getting new APIs on the platform, so we could do more with images and with the network. And lots of applications which were desktop only started coming to the web. Gmail is a perfect example. It came about at the same time when Chrome, and V8 engine was actually what made possible to run Gmail on the web. So today, we all added documents and sent emails from the browser, but there are still areas where JavaScript performance is a struggle. So video games were an early goal of WebAssembly, not because we all want to play video games on the web, but because getting to that level of performance would enable you to bring many other applications to the web. So think for a second about software that you need to use outside of the browser. It could be video editing, or maybe music production, or 3D rendering, virtual reality, image recognition. And the list goes on and on. Oops. Spoiler alert. OK, So why would you need all that on the web? Why is the web so attractive? To me, web is kind of like magic. It just works anywhere. No download, no installation, and it has safety baked in. Browsers have sandboxes, which keep the code running in them from messing with your system memory. So you never think twice when you visit a website, but you wouldn't just download a random binary and run it on your computer. And then my favorite thing of all is the ease of sharing on the web. Links are just clickable strings, which you can put anywhere. And we all know that's not how app stores work. And for us developers, it helps that web is a universal platform. It enables you to run your application on almost any device, which also means that you need to maintain a single code base, and it makes updates much easier. So because of all of this, we went from text and links to this amazing platform filled with powerful applications. But it's still powered by a language which wasn't designed to do all of that. So here's what WebAssembly brings to the table. I'm going to focus on three things. That's speed, portability, and flexibility. Let's talk about speed. WebAssembly is a low-level binary format. This is what it looks like. It has a textual representation. You can write it by hand if you're really adventurous, but really it's only meant for debugging. The binary format is what you deliver to the browser. So binaries are much smaller than textual files. That makes them faster to download, which is really important on slow networks. And JavaScript's textual format also means that the browser has to parse it. Parsing is not that easy thing. Turning text into binary format involves quite a few steps. There's lexing, tokenizing, then turning that into abstract syntax tree, and only then you get to the binary format. But now remember, WebAssembly is binary. That means no parsing. You just decode it, which makes things much faster. And now, JavaScript is dynamically typed. When you type x+1, you don't really know what x is. It could be a number, it could be a string, maybe a Boolean, and you don't compile that code. You just give it to the browser to figure it out. This makes it fast to write, but it also means that the browser engine has a lot more work to do. It has to figure out what types are you planning to use, and it has to guess it. And sometimes, if it makes a wrong guess, it has to optimize the code all over again for the actual type that you're using. Now, WebAssembly, on the other hand, is statically typed. That means the engine doesn't have to speculate which types you're running, and most of the optimizations can happen in that initial step, compilation from the source code. WebAssembly also gets a speed boost from streaming compilation. Kind of like when you watch a YouTube video, you can watch it as it's downloading. The same thing with streaming compilation. Browser compiles your code as it's being downloaded. For smaller binaries, that usually means they're ready to run as soon as the download has finished. All of this makes WebAssembly fast. But it's not like JavaScript cannot be fast. It's just that in order to make JavaScript that fast, you have to write it in a very special way that works with the browser engine optimizations. And the thing is, we have different browser engines, and they do not optimize things in the same way. So if you optimize your code for some specific quirk of a V8 engine, it might mean that it will run slowly in Firefox's SpiderMonkey. With WebAssembly, there's no guessing. It's statically typed, and you just give it to the browser, you get reliable performance, and I think that's what makes it so attractive. And then there's portability. How do you take a thing from one place to the other and have it just work? This was really one of the important design goals for WebAssembly. So just so we're all on the same page, let's go over that design quickly. Assembly typically refers to humanly readable languages that are kind of similar to machine code. Machine code is what your processor understands. It's a bunch of numbers. Now, every high-level programming language has to get translated down to machine code in order to run on the processor. And different processor architectures have different types of machine codes and a different assembly for each of them. Now, even though it's called WebAssembly, then it's not quite an assembly language because it's not meant for any specific machine. WebAssembly is a language for a conceptual machine that's the least common denominator of popular real-world hardware. It's for the browsers. And when you deliver code for the browser, you don't really know which machine it's going to run on. So the browser takes WebAssembly code and quickly turns it into any machine's assembly. Now, the thing with portability. To run an application on a device, it has to be compatible with device's processor architecture and operating system. That means compiling code for every combination of a processing architecture and operating system that you want to support. But with WebAssembly, there's only one compilation step, and your app will run in every modern browser. Now, good use cases for this are porting legacy applications to the web, or porting open source libraries from different languages to the web. C++ is a really good example because it's a language that's been around for a long time. It has many open source libraries, which you can make available on the web. It's also supported on practically every platform, iOS and Android. So you could have a single code base which can run on a host of devices. And then another really exciting thing is flexibility that WebAssembly brings to the web. Until now, you could only truly use JavaScript to be fully supported. But now us web developers can choose other languages to try. And then there's another thing. Other developers who don't know JavaScript can now be able to write applications for the web. That means more developers with vastly different perspectives and experiences. I think that diversity is always a good thing, and it will bring more exciting things on the web. Now, here's how WebAssembly is flexible. It compiles into modules that you can embed into your applications. They have imports and exports, kind of like regular JavaScript objects. So you can call a WebAssembly function from JavaScript, and you can call a JavaScript function from WebAssembly. So really, WebAssembly is not a replacement for JavaScript. It runs alongside JavaScript. And JavaScript is really good at a lot of stuff. New frameworks are very efficient at DOM manipulation, for example. So sticking to pure JavaScript will probably be both easier and faster in most cases. But because they work together, you can choose to write some very specific core functionality in WebAssembly and then have the user interface in JavaScript. Or if you're, for example, struggling with performance bottlenecks in your existing applications, you now have the option to use a different language that's better suited for the problem. It really comes down to using the right tool for the job. Fully supported languages are C, C++, and Rust, but many others are in the works. .NET and Go already shipped experimental support. And then there's one language that's really interesting to me, and that's TypeScript. AssemblyScript is a way to compile TypeScript programs to WebAssembly. But you can't use just any TypeScript. It has to be strictly typed. I think this is awesome because as a web developer, I do know a little bit of Rust, but I'm still much more comfortable with JavaScript. And I'm sure all of you, even if you haven't tried, you could easily pick it up. So TypeScript gives us a chance to try WebAssembly and see if we can benefit from it in a pretty easy way without having to relearn a totally different language. Moving on to how this actually works. You need a tool to compile your programs. So this dragon is a logo of a really old compiler. It's called LLVM. It's very powerful. It's modular. You can set it up to work with many different languages. But of course, there are easier ways. Mscripton is a tool which is based on LLVM, and it's used for compiling C and C++ programs. And then Rust has its own compiler, Rust-C, which can output WebAssembly directly. And the cool thing is that it has this companion WASM pack, which enables you to easily package your modules for publishing. So here's what that kind of looks like. If you compile a C file with Emscripten, what you get is a WebAssembly module, but you also get HTML and JavaScript files. You need them because WebAssembly can't really interact with any of the platform APIs. That means the DOM, WebGL, or WebAudio. To reach any of these, and even to display the output of your WebAssembly program, you have to go through JavaScript. Emscripten sets up this boilerplate code, which allows you to do that more easily. And then you load that JavaScript file in your HTML, and then output your WebAssembly output in a text area or a canvas element. Now, this is a command that would enable you to do that with Emscripten. Now, MCC invokes Emscripten. Hello.c would be your source file. Then you tell it you want wasm equals 1. -o hello.html means output it to an HTML file. Wasm bindgen is a tool which makes this a little bit easier for Rust, and it's going to make it easier for other languages too, because it's really designed to be language agnostic. But right now, it's really not the smoothest process. And there are a couple more tricky things. WebAssembly has only 4 types, and they're all numbers. This means if you want to pass more complex data types between JavaScript and WebAssembly, you have to, maybe if you want to pass a string, you'd have to encode it into an array of numbers and then pass a pointer to it. It also doesn't have direct access to external JavaScript variables. And also, making a lot of calls through JavaScript is not really fast now. Firefox, for example, has done a great job in mitigating that, but other browsers still have catching up to do. For now, good advice is to use WebAssembly to offload big chunks of work. Those could be resource-hungry tasks, like maybe resizing an image or processing an audio stream. So you're all probably wondering now, are people using it? And the answer is yes. If you've ever tried to upload a huge raw image to Facebook, it went through WebAssembly code. libjpeg is this really old open source library for processing images that's used very widely today. They compiled it to WebAssembly and now use it to upload your huge photos and compress them for publishing. And if you ever play an audio file on Wikipedia, they use open source codec called Opus for processing that, which is also compiled to WebAssembly. And then recently, Skia, the open source graphics library, which powers both Chrome and Firefox, has been compiled to WebAssembly in a bit of a smaller scope, but still it allows you to test new Canvas and SVG APIs on the web. And then there are hybrid apps, which I mentioned, where only parts are written in WebAssembly. Squish.app is an example from Google, which is used for image compression. So you upload your image, and then you can select several compression types, which are not really all available on the web, like MozJPEG or WebP. Now, these compression algorithms are implemented in WebAssembly, but the user interface is written in Preact. It makes it very lightweight, and the entire application loads really fast. You can try it on your mobile phones right now if you visit squish.app. And bigger apps use the same approach with WebAssembly too. Figma is an interface design tool. It runs in the browser and allows designers to easily collaborate and share their work between each other. It has a pretty powerful 2D rendering engine, which is written in WebGL. It can handle really large documents. It was written in C++ and compiled to WebAssembly. But the user interface, that part is in TypeScript and React. And then I also mentioned legacy applications. One good example is AutoCAD. This is a design software which engineers use to make floor designs or piping designs. It was written in C++. It's been around for a really long time. It's older than the web itself. So AutoCAD team has been able to rewrite this huge application with hundreds of thousands of lines of code and just port it to WebAssembly. They did not have to rewrite any single thing. And it's now available in web browsers, and their users can access it on pretty much any device. And people are also doing weird stuff. Someone ported Windows 2000, so now we have an operating system running in the browser. And yes, you can totally play pinball in it. Now, WebAssembly is supported in all major browsers. That means for 86% of all global users. There is a standards committee, and they're all very committed to making it work. This is really different from how things were in the past. Some of you maybe remember these images, Flash or Java applets. But the younger crowd here probably never even heard of this. And that's because these technologies are dead. They've been pushed by competing companies, and they were really never part of the web platform. That means they had different strategies, they didn't play along, they didn't integrate well, and eventually all of them died off. But WebAssembly, on the other hand, is standardized. It's part of the web platform. It integrates well with JavaScript, and all browser vendors are very committed to working together, to implementing new features, and to standardizing all of that. So, what are the benefits of all of this for JavaScript developers here? I'd say we get all the best modules. This integration with JavaScript makes it more powerful because we get all the best libraries from all the different languages available to us to use in our JavaScript apps. I think JavaScript in part expanded a lot because of NPM and the ease of distributing modules. The thing is, WebAssembly modules are also published on NPM. There are 600 modules available already. So you can, in future, you will be probably able to easily use all sorts of different modules directly from NPM. And if you really think you are not going to need that, you have absolutely no intention to write a video game or to build the next Photoshop, well, in that case, WebAssembly can help you too, because a lot of developers' tools get a good boost from using WebAssembly. For example, this is already happening. Source Maps library, which powers Firefox DevTools and Webpack, has been rewritten in Rust and compiled to WebAssembly. This rewrite made it 11 times faster. And then, for the frameworks, Ember is investigating implementing its Glimmer virtual machine in Rust, so it can compile it to WebAssembly. And there's like another popular framework too, React, which could really benefit from rewriting some parts in Rust, like the diffing algorithm, which can be easily parallelized. And what else is there? What else can WebAssembly do? WebAssembly has started expanding beyond the browser. So WebAssembly right now runs inside of browser engines, but really it's an assembly language for a conceptual machine. So you can create other runtimes which can run WebAssembly on a different operating system. And that's exactly what's happening. Fastly and Cloudflare now run WebAssembly in the cloud, and then there's also Wasmer, which is a universal WebAssembly runtime. So this WebAssembly thing obviously works. Let's see what lies ahead. It's going to get even better. All browsers are already working on implementing new features. Support for threading is almost there. It's available in Chrome Origin trial, and Firefox has implemented it too. It's just currently disabled due to some implementation bugs. And garbage collection is also coming. I think it will come probably next year in Firefox. This will make WebAssembly a better suited target for languages which include garbage collection, like Java, for example. And another really important goal, which will make working with WebAssembly easier, are better debugging tools. So another interesting thing is support for script type module, which is going to be implemented soon. This will allow you to just embed your WebAssembly module using a script tag. So this is a JavaScript conference, and I really want to reiterate that I think JavaScript is a great language. It's flexible enough to build almost anything. I think it will still have its place in web development. It's just those few gaps that it cannot handle well can now be handled by WebAssembly. So WebAssembly is definitely not the end of JavaScript. I think it's a new beginning for the web. Thank you so much for your attention. If you want to learn more about inner workings of WebAssembly, I can really recommend you Code Cartoons by Lynn Clark. And maybe if you want to go through this presentation at your own pace, you can check out my article, WebAssembly, How and Why. If you have any questions whatsoever, I'd really love to talk to you all, and I'll be right here as soon as I step down from the stage. And I just want to say diakui, and really looking forward to meeting you.
Thank you.